Hi, everybody. So, if I were not a computer scientist, I would have been a historian. So, this talk will enable me to indulge in my second career. Okay. So, there's this new excitement about deep learning, but I'm going to start with a history lesson. There is this exercise of when will computers be as brainy as brains? And I mean, we can all have our opinions on this, but I think the most serious work that I have seen on this is back in the 1990s by Hans Moravec. And Hans Moravec did some calculations of, based on some assumptions of when will the brain power of computers be equivalent to that of the human brain. So, he made some assumptions, and you can quibble with these assumptions, and you can be off by probably by a factor of 10 easily based on this. But we believe in orders of magnitude reasoning, so this is good. So, he made some assumptions about clock rates of neurons, what a synapse contains. So, therefore, he comes up with some number about the information processing rate and storage of the human brain. And then he tries to extrapolate based on what was known in the 1990s, assuming Moore's law of how computing and storage would grow. And he in fact claimed that 2000 to 2025 you would have that human level computing power available at a desktop machine. And here are some actual plots where these are both x and y axes here are exponential scales. So, this is megabytes of storage and MIPS of computing power, and he puts the brains of various entities, in artificial as well as biological, on that scale. So, somewhere up there you have like a billion MIPS, which would be, I guess, 10 to the 12 instructions per second. And then this is a curve. So, I really commend him for this, because he made these extrapolations. It's in the political sphere, we know that there are people who make predictions and they hope to get away with it because they think nobody will check them up. So, our former Vice President Dick Cheney made pronouncements about what would happen, and we can now of course go back and check whether reality matched up with the predictions. So, this is true for scientists too. So, these are predictions from him based on curves of prediction of computing power, etc. And basically this is what the computing power should be available for $1,000. So, a million up there, so million MIPS, so 10 to the 12. And this is not far off from where things are. So, we would, if we were putting in today's data, we would get to it's consistent with that curve. So, 2025. Now, of course, we do not have to work with a single computer. We can work with a cluster of computers, and I mean places like Google and Facebook and Microsoft and so forth, and Amazon. I mean, the cloud computing is here. We have we use thousands of machines, millions of machines. So, in fact, this computing power is available today. So, I would argue that the deep learning revolution is in a way the natural way to exploit this technological trend. And that's all there is to it, really. Okay. And Moravec plotted out the computing power available to various computer programs. This is from the 90s, and for chess there is a very nice curve, and at the point where it matches up with human capability is about the time when a chess program beat Kasparov and became the world champion, which is around late 1990s. Now, chess is trivial compared to thinking, right? Compared to perception and action. I have always claimed that the important thing in AI is what a child can do by age 3. Everything after that is relatively easy. And by 3, what a child can do is perception and action and language. And this is where all the difficulties are. Now, so chess machine performance. Now, what did AI people do? Well, they start the enterprise of AI starts in the 1950s with this conference in 1956, and obviously computing power was nothing, right? I mean, you have to run Moore's law backwards to think about computing power at that time. So, essentially they did not think in terms of replicating the brain, they thought they were smarter. They were all mathematicians to begin with, and mathematicians come with natural conceit. So they thought that they would be able to cleverly model their way out of it. So the logic tradition, the symbol processing shortcut, and this is in fact what was tried. So the goal in the 60s and 70s in AI was to just cleverly model reality and find these compact descriptions of the kind that have been unreasonably successful in physics. Okay, this failed. Okay, now we know clearly it has failed because we tried for 50 years. Here is this other tradition which also goes back to the 40s and 50s. This is McCulloch and Pitt, which is taking biology seriously, taking the brain seriously, constructing models of it, somewhat abstracted from the reality, and then going off from that to build machines. McCulloch and Pitt's 1943 paper is a classic. Hebb's paper from 1949 is a classic. And just continuing on with, I'm mentioning essentially neuroscience and theoretical neuroscientists. Work from Hubel and Wiesel, this is on for which they got a Nobel Prize. This is for the cat and monkey orientation selective cells in the first area of visual processing. So vision is something like 50% of the brain. And they had these observations, and then someone called Fukushima used this as a model neural network with many layers, modeled after the hierarchy in a human or primate visual processing system. And he had these layers of simple cells, complex cells, and so forth, culminating in neurons which might respond to faces or dogs or what have you. 1980. Okay. So we have this disconnect between what the computing power will let us do and where sort of the modeling ideas of people inspired by neuroscience are going. And there was this Fukushima work of 1980 led to convolutional neural nets, which is basically the Fukushima architecture but trained using backpropagation. So they in fact threw away one bit of biology, which is Hebbian learning, which is what Fukushima had, and put in backpropagation, which makes sense from an engineering point of view, but is not necessarily justified by biology, and they showed it worked for digits. Well, in the period of 90s and 2000s, these kinds of neural networks were not so popular because they were difficult to train. They always involved non-convex optimization, which is a bit of a challenge. But basically, the Krzyzewski, Sutskever, and Hinton paper from 2012 showed that no, this is not true. Stop worrying, and there's this old movie, Stop Worrying, and How I Learned to Stop Worrying and Love the Bomb. So the title of this paper could have been How I Learned to Stop Worrying and Embrace Non-Convex Problems. Okay. And I was a critic, and I was changed by these empirical results. And they showed that you combine today's GPUs, you combine today's data and today's computing, and you can make this work. Then there was a debate about whether this worked for anything more than full image classification. In a robotic setting, we are really interested in objects. Can it work there? And the answer is yes. And work at Berkeley contributed to that. And of course, this is being done everywhere. I'll just show you one slide which indicates what's going on. Sorry, I went back. This is a slide of progress. X-axis is time. Y-axis is some accuracy on an object detection task. And it was kind of stuck around 35% for the late part of the 2000s. And this RCNN work, which is from Rosker, Sheikh, Trevor, myself, and Jeff Donahue, the number went up to about 60%, but today the number is in the 70s. But this is one task of finding objects in image and localizing them. There are many tasks where you can plot similar curves. Okay, and I'll conclude with the capabilities relevant to robotics. So in a robot, we are going to a robot which is doing manipulation and locomotion will typically be equipped with some capability of depth. So it could be an RGBD sensor, it could be stereo, what have you. So we can ask directly the question, if we have RGB D. So RGB is red, green, blue, D is depth. And you can get this with Kinect, LiDAR, or with stereo. I mean, that's a detail. What can we do? And here's a pipeline from our group where we start with an image. Then below it is a depth map where red means close to you, blue is further away. And here is sort of the whole pipeline for understanding the scene, which is a prelude to manipulating it, moving around in it, and so forth. So you have you generate region proposals, you detect objects, you segment out the scene into different objects, you estimate the poses of objects, so which way is the chair facing in terms of this. And in the final understanding is, we've taken this image and we've converted it to renderings of 3D models of these object classes. And here are the kinds of results you get. So these are general images of rooms and so forth. So the beds have been isolated, but they have also been segmented out. It's not just that you're saying somewhere in the image there's a bed. There exactly is the bed. So that purple is the highlighting of the object. So your robot has that understanding now. And this slide shows how we can estimate pose. So what has been done here is that we have matched the chair or the bed or the sofa to a 3D model of the chair or sofa or bed and oriented it in the right way. And that's shown in the third column or the corresponding thing on the right side. And the accuracy numbers are in the 70% kind of range. So we need to do even better than that, but I think that will happen. So robotics has both perception and action. I mean, vision and robotics are intimately coupled. Until we had the computing power of today, we were always taking shortcuts. And the time has come to get rid of the shortcuts, just do it right, and it will happen. Thank you.